Okay, so two more fairly straightforward results about null spaces of powers of t. So in the last clip, we showed that if you ever have it so that the null space of t to some power is equal to the null space of t to the next power, then it stays flat, like it never grows again. They're all constant all the way up. And so in this result, we're going to show that n is always good enough to make that flattening happen so that the null spaces stop growing. And then we'll, after that, we'll show that v is the direct sum of the null space of t to the n and the range of t to the n. And so we've seen, for instance, that if you have a projection, then v is equal to the null space plus the range of that projection. That's not true for a general operator, but if we raise those operators to the nth power, where n is the dimension of the vector space, then it is true. So we'll see that. Okay, so let's go back and let's prove the first one. So we want to see that these vector spaces stop growing once we get to the nth one. And so this is, we're basically invoking our previous result, 8.3, to see that it suffices to show that the null space of t to the n is equal to the null space of t to the n plus 1, and then all the rest will follow from there. So by way of contradiction, suppose not. Okay, so we know that each one is contained in the next, so we know that it's definitely true that the null space of Tn is contained in the null space of t to the n plus 1. And so I'm saying this is contained but not equal with this symbol right here. So strictly contained in, so it's a proper subset. And then remember, once you get to a place where there's an equality, it's equals forever after. So if there's not an equality at the nth step, then that means that there's not an equality at the n minus first step. And all the way back. Whoops. Right? And then this, I guess, actually all the way back is really all the way back when we get to the identity, which is t to the 0, which has null space equal to 0. Okay, so then we've got this. So now take a look at this sequence. Since the dimension of the vector space in question has to increase by 1 at every step, that means that when we get to the end, we have the dimension of the null space of t to the n plus 1 being at least n plus 1. So now the null space of t to the n plus 1 has a dimension strictly larger than v, which it's a subspace of, and that is absurd. So there's the thunderbolt of contradiction. And we are done. Okay, so let's see. So now on to the next one. In order to show this decomposition right here, first we're just going to talk about this direct sum, and we'll show that this sum is direct, and then we will prove this equality. All right. So so first we show the sum is direct, and then we show v equals the sum. So to see the sum is direct, we'll take something from the intersection. So let v be in the null space of t to the n intersect the range of t to the n. Okay, so what does that mean? So then the fact that it's in the null space means that t to the n applied to v gives you 0, and the fact that it's in the range means that there exists a u such that t to the n u is equal to v. All right, so what can we do with that? Well, now if I do t to the 2n applied to u, so in other words, I'm applying t to the n to both sides of this equation right here, then this is t to the n v, but t to the n v we chose to be equal to 0. So then that shows that u is in the null space of t to the 2n. But from our previous result, we know that t to the 2n is equal to the null space of t to the n because it stops growing at the nth iterate. And so then that means v, which is tnu, is equal to 0. So now we have that the sum is direct. All right, so now if we look at the dimension of the null space t to the n plus range t to the n, we can use a dimensional argument to see that this is actually equal to v. Why? Because it has the same dimension as v, and a subspace with the same dimension has to be the same space. So this is the dimension of null space t to the n plus dimension null space range t to the n by 378. Whoops, since the sum is direct. So 378 is the one that says that if you have a direct sum, then the dimension of the sum is equal to the sum of the dimensions. And then if we look at this, this is exactly the form of the rank nullity theorem. So this is equal to the dimension of v by the rank nullity theorem, 3.22. And so, as I mentioned before, now we have a subspace of v which has a dimension equal to the dimension of v, so it has to be v, and we're done.